Hello from Chem Help ASAP. This video is a review of the various common addition reactions that students encounter during a two-semester organic chemistry sequence. This video will not cover every reaction in every class, but it should definitely include the most common reactions. If I have omitted your favorite or your instructor's favorite addition reaction, then please let me know and maybe I will make a follow-up video. Finally, this video is intended to be a review and is recommended for students who have already learned some organic chemistry as opposed to students who are new to the subject. It is a review, not a preview. Addition reactions normally get extensive coverage in both semesters of college organic chemistry. Additions involve the net loss of a pi bond and net gain of a sigma bond. So here is a simple hypothetical addition reaction scheme. From a bonding standpoint, in the starting materials, we have an XY sigma bond and an AB pi bond. Both of those break during the reaction. We form an AX sigma bond and a BY sigma bond. That gives a net change of one broken pi bond and one new sigma bond. Energetically, pi bonds tend to be weaker than sigma bonds. So breaking a weaker bond, the pi bond, and replacing it with a stronger bond, the sigma bond, gives a favorable reaction. Delta G is negative. Note that the opposite of an addition reaction is an elimination reaction. You gain a pi bond with the net loss of a sigma bond. When looking at addition reactions, there are many different ways to classify them. You can think of them as redox reactions. Many addition reactions have regiochemical considerations. You can discuss the type of pi bond involved in the reaction. You can also think about the stereochemical outcome. As we move through the addition reactions through the remainder of this video, we will discuss each in the context of these different classifications. Let's start with alkene reductions. In all cases, if possible, we will use cyclic alkenes, which are better for visualizing the stereochemistry of the reaction. So we're talking about alkenes. These are CC pi bonds. Furthermore, both of these additions are reductions, and we'll need to talk more about that. The first reaction is a hydrogenation. We're adding H2 across the CC pi bond. Anytime you add two electropositive atoms, these are atoms less electronegative than carbon, add electropositive atoms to an alkene, you get a reduction. Hydrogen is less electronegative than carbon, so adding hydrogen is a reduction. Based on the mechanism of the reaction, which involves a palladium catalyst, the two hydrogens are both added to the same face of the alkene. I've shown the top face. Both hydrogens are up, a syn addition. Because the same atom is being added to both sides of the alkene, there is no regiochemistry to discuss. The next reaction is a hydroboration. You'd never run this reaction to get this as a final product, but I think it's worth inserting here. The hydroboration involves adding borane and H on one and BH2 on the other alkene carbon. This is a syn addition. Both bind to the same face of the alkene. I've shown the top face. Since boron is less electronegative than carbon, this is also a reduction. Because BH2 is larger than hydrogen, the BH2 favors binding to the less substituted carbon of the alkene. Therefore, the hydroboration is regioselective. We'll return to this reaction in a couple slides. Let's talk about HX additions to alkenes. These involve additions of H and X, a halogen, across the alkene pi bond. These reactions normally require just HX, a mineral acid. The reaction starts with protonation of the alkene to make a carbocation. The resulting carbocation is attacked from either the top or bottom face to give the product. Since one atom, H, is less electronegative and the other, the halogen, is more, this reaction is neither an oxidation nor a reduction. If there is a substitution difference on the two sides of the alkene, then the protonation will form as stable of a carbocation as possible. That sets up the regiochemistry of the product. So the halogen ends up on the more highly substituted carbon. Finally, this reaction typically shows no stereo control. So no stereo, because the carbocation will be attacked from either the top or bottom face. So this is neither syn nor anti. In this scheme, I'm assuming the proton was added on the top face of the alkene. The halide can then end up on the top or bottom. So this is no stereo control. The same reaction can be performed under radical reactions with hydrogen peroxide. This completely changes the mechanism. The reaction is still an addition of HX, still neither an oxidation nor reduction, still neither syn nor anti, but it does have the opposite regiochemistry. The halogen finishes on the less substituted side of the alkene. Alkene hydration is another common addition reaction. The first type, the acid-catalyzed hydration, is much like the HX addition from the previous slide. The reaction involves a carbocation, and water attacks the cation non-selectively from both the top and bottom faces. So this is not an oxidation or reduction. Like other additions involving carbocations, the carbocation forms on the more highly substituted side of the alkene. So there is regioselectivity to this reaction. The products drawn show the Markovnikov alcohol. Just like HX additions, there is no stereo control in the reaction. Another hydration involves the previously mentioned hydroboration. We've already talked about this first step. It is a reduction and a syn addition. When we pair this hydroboration product with an oxidation step, the BH2 is exchanged with an OH group. Since we have now replaced the boron with an oxygen, the overall transformation is now neither an oxidation nor reduction. The added H and OH are still on the same face of the alkene, so this is a syn addition. Note that compared to the acid-catalyzed hydration, the OH is on the less substituted carbon, and the regiochemical outcome is the opposite. This lower product is the anti-Markovnikov product. Let's now discuss the alkene oxidations. All of these involve CC-pi bonds. All are oxidations because we are adding 2 sigma bonds to electronegative atoms. We still need to discuss regiochemistry and stereochemistry for each reaction. For the dihalogenation, I'm showing a dibromination. We're adding 2 bromines, so there is no regiochemistry. The stereochemistry is an anti-addition, and this outcome is driven by the 3-membered ring bromonium-ion intermediate in the reaction. For the epoxidation, again, there is no regiochemistry. Since both CO bonds are on the same alkene face, I've shown the top face, the addition is technically a syn addition. For the dihydroxylation with something like osmium tetroxide, you add 2 OH groups. There is no regiochemistry, and the reaction is a syn addition. Finally, in doing hydrohalogenations, you do encounter both regio and stereochemistry. In the reaction, the bromonium intermediate is opened by water. with the water attacking the more highly substituted carbon, this sets up the regiochemistry with the Br on the less substituted side of what used to be the alkene. The OH and Br are on opposite sides of the molecule, so this is an anti-addition. Let's now switch to carbonyl additions, additions involving CO pi bonds. In contrast to the alkene additions, which typically are electrophilic additions, an electrophile reacts with a pi bond, carbonyl additions tend to be nucleophilic additions. Nucleophiles react with a pi bond. The nucleophiles on this slide are hydride, from sodium borohydride or lithium aluminum hydride, and organometallics, like a Grignard reagent. Both of these reactions are technically reductions because we're replacing a CO bond with a CH or CC bond. There is no syn or anti aspect to these reactions, but there is regiochemistry. The nucleophiles always attack the carbon side of the CO pi bond. Additions to imines are very much the same as carbonyl additions. They are formally reductions. Regiochemistry involves attack on carbon, not nitrogen. Since we can incorporate a CN pi bond in a ring, you might think we can show off some stereochemistry. Well, we can't. The nitrogen with its lone pair is not configurationally stable, so the NH is able to rapidly switch from up to down and back again. Therefore, we can't classify these additions as syn or anti. The last slide hits two different additions. First, we have the Michael addition. The Michael addition involves a CC pi bond and is actually a nucleophilic alkene addition, not an electrophilic addition. A nucleophile, like an amine, can attack the beta carbon of an alkene that is attached to a strong electron withdrawing group. There is regiochemistry because the nucleophile will always attack at the beta carbon relative to the EWG. The reaction has an enolate intermediate, and the addition of the proton on the alpha carbon is rarely stereo-controlled. This particular Michael addition would not be a reduction or oxidation. In the second reaction, we have a Diels-Alder cycloaddition. This addition is distinctive because you have a net breakage of 2 pi bonds and a net formation of 2 sigma bonds. The reaction also makes a ring, hence the cyclo in cycloaddition. The addition occurs in one step and is a syn addition. It is not an oxidation or reduction, just breaking and making CC bonds. The regiochemistry of the reaction is controlled by electronic bias in the diene and dienophile, so regiochemistry is a factor in the reaction. For this reaction, both regioisomers are shown. In this case, the left-hand regioisomer would be the favored product in the reaction. Okay, that was a lightning quick review of different addition reactions with consideration of regiochemistry, stereochemistry, and changes in oxidation state. Thank you for watching until the end. Please leave a comment, leave a like, or subscribe to the channel. Take care.